Right, good afternoon, and welcome to this afternoon session on advanced electronics of the Nano Symposium. Special welcome to the students in my class who are sitting here. Extra credit for all of you. Thank you for all right, it's been very exciting in the last few years to be in the world of microelectronics and semiconductors. And as you know, it's been on the news just about every week with news of one kind or another coming from all over the world. And part of it, as you know, is from the tremendous disruption that happened as a result of COVID in the last 3 years or so. I'm sure you know this number. In 2021 alone, there was over $200 billion of cars that were not sold because they were lacking chips. Everything was in place except the chips. Altogether, across all industries, $500 billion worth of stuff were not sold in 2021. And so this was a very severe disruption. And it happens because modern systems have a lot of chips. In fact, cars have somewhere between 500 and 1,500 chips in one car, depending on how advanced it is. And on average, about 40% of the cost of a car is in the electronics. And you can imagine how that is going to increase as we move into widespread dissemination of electric vehicles. So this is, it's become very clear that this is a strategic technology from a commercial point of view, but also from a defense point of view, and that as a result, governments really want to ensure that they will have an uninterrupted supply of the most advanced chips, but also of what are known as legacy chips, chips that are made on older technologies, but that are commercially very important, as is the case of cars. Cars use not the latest technology, but a few technologies back. So all those technologies are really important. So as a result, we have seen in the last few years huge government incentives to promote semiconductor manufacturing on the home soil. In the United States, depending on how you count, as much as $79 billion are going to be dedicated in the next 5 years to foster semiconductor manufacturing in the US. In Europe, it's still under discussion, but they're talking about 43 billion euros, and so on around the world. Now, these big investments are already, they are still announcements at this point, but they are already doing its magic. So for example, in the US, just in the last couple of years, there have been announcements from companies that they will invest over $200 billion of manufacturing facilities on US soil. These will be 23 new fabs, again, from commercial companies from all over the world. So clearly there is going to be a huge impetus in expanding semiconductor manufacturing in the US and across the world. So the future looks very bright, not just because of all the interest and because of all these investments, but also because the technology continues to move at an amazing pace. In fact, it's kind of interesting. If you dig through the literature, you will find that Moore's law has been dead for what, 15 years or something like this, which is strange because we have seen and we continue to see amazing progress in all semiconductor technologies that enter all kinds of systems. In fact, I asked my friends in industry that are working on some of the more advanced technologies, how many years ahead do you see in terms of, look at your roadmap, new technology generation that you guys are developing going forward, how many years do you see? And they all tell me 10 years. Very easy, there's 10 years of future technologies that are going to come. Now, they told me this 10 years ago, and I'm sure they will tell me this 10 years from now. So there is clearly many problems and many challenges, but you know, this is an extraordinarily innovative community that continues to find ways around these problems. So this is the topic of this panel, is advanced electronics and its prospects, and in particular, I want to focus on 3 points. First, I would like that our illustrious panel outlines from their point of view new directions that they see going forward in semiconductors and microelectronics. From my point of view, clearly there are new materials and new devices and based on new physical principles that are going to be involved. So it's innovation is going to be really critical. So I'm very interested in seeing their perspectives. Now, excellence in innovation is not enough. We need to be also excellent in translating these innovations to the marketplace in an expeditious way. So I also want to hear the perspective from our colleagues here. And then finally, I want to also be able to talk a little bit about long-term leadership. Not just now, not just over the next few years, but long-term leadership in all various strategic technologies that we're talking about here. All right, so we're going to move into the panel. Let me start from my left here. We have Doug Carlson, who is the Senior Vice President for Technology at MACOM. Then we have Susan Feindt, who is a Senior Fellow at Analog Devices. We have Jing, who's Professor of Electrical Engineering and Computer Science at MIT, Ruonan Han, Associate Professor of Electrical Engineering and Computer Science, and Kevin Chen, also Assistant Professor in ECS. So to get things started, I have a question for all of them, but in general, I don't think we want all the questions to be answered by everybody, just focus on whoever is the greatest expert on any one topic. But for all of you, from your vantage point, we're going to start with Doug. What are the most exciting new directions in semiconductors and microelectronics with potential for revolutionary progress ahead? Doug.
Sure. So to give a little context, people should understand MACOM is really a RF and optical company. So my perspective is going to come from that point of view. So without a doubt, in our field, the biggest and the most exciting thing is really wide bandgap semiconductors, gallium nitride, all of these things. And when you think about the origin of GaN, which was probably back in the early 1960s, we're now making devices and they're in the market today in the 2020s, but we're only at the very beginning of understanding how those can work at optimizing, making better and better devices and better solutions. Because really, our role in the world of semiconductors is connecting the digital world to the real world, right? So things that revolutionize that connection, so power, size, ability to manipulate those signals is what's really, really key.
Mm-hmm. Susan?
First, I want to say thank you for having me here and happy anniversary. I remember just being in a hard hat tour of the facility and look where we are today. So that's amazing. And it's amazing in general, the awareness and the focus on microelectronics. As you said, Jesus, it's incredible. I think my family now knows that what I do is relevant, which is good. And I think that the investment that the CHIPS Act is going to bring to R&D and manufacturing will enable and accelerate innovation in key areas that are going to be driven by megatrends in the industry, such as the electrification, AI and automation, remote health, security. All of these things are going to be, accelerating and driving new technologies. And especially technologies at the edge, and Doug already said it, but analog too is we translate real world phenomena and digitize it and process it and interpret it. So this whole move to edge electronics and smart edge solutions, it's ripe for what analog devices does. We've always been a more than more type company. And so the things that we're interested in are the convergence of bio and microelectronics is going to revolutionize the telehealth and less invasive surgery by either having ingestible or implantable or wearable devices. I think that it's going to, like I said, it's going to be disruptive and revolutionary what you can do by combining miniaturizing sensors with microelectronics, with AI and data analysis. The other area is, I agree, compound semiconductors has been there for a long time, but I think it's now coming to the forefront, and especially with things for RF and for power, technologies like wide band gaps. They're going to require material innovation, device innovation, package solutions to address thermals and other phenomena, and that's really going to be interesting. So there's a lot of exciting things coming, and I know that Vladimir talked about a lot of them this morning too. So,
thank you, Jing.
So for me, I'm really thankful to be in this occasion and celebrating the MIT.nano together. So my research group, we work on materials, and particularly materials that's also for these in the microelectronic devices applications. And I like 2D materials, nanomaterials. And I see that the future, like this morning we had quantum computing panel discussion, and no matter is microelectronic, the traditional computing or the quantum computing or neuromorphic computing, etc. All these needs new materials for new devices to address this, and it's a very exciting time for us as well. Yeah.
Mm-hmm. Ruonan?
Well, first of all, thank you for having me here. Microelectronics to me are very exciting in basically, I would say from two aspects. My own research is RF integrated circuit design, especially I'm focusing on high frequency, like terahertz. And I think what really these semiconductor microelectronics enabled us to do is not only just to make things possible. For example, in my case, we try to make the handshake between microwave and infrared or light by bridging the gap. Now the speed of these devices are getting so fast that this is becoming possible. And but not only just that, but also these devices or these technologies are making things so cheap, so that we start to really enable applications that are truly practical. So that is really fascinating to me. And also on the other hand, as a professor, I train students. We also use these chips as tools so that the students not only just learn circuits, but also in order to investigate the different applications, they should also study different physics, chemistry. So we also bring this interdisciplinary training into the picture as well, which I think is also something that I didn't expect before taking this job, and I think that's also what I like.
Kevin?
Right. So first of all, I'm super happy to be here. I want to approach microelectronics from a sort of a new perspective, in the sense that we've heard about a lot of exciting news about innovation in computation, how microelectronics is used to do computation, process information. But as a roboticist in MIT, my lab works on insect scale robot. Those robots are really on the edge. Think about honeybees or spiders that crouch on walls or land on flowers. One of the critical things for those micro-scale robotic systems is that they actually need a lot of energy or power to operate. So as opposed to thinking about processing information, what we realize is that on those micro-scale systems, 90% of the energy is spent for locomotion, flying, swimming, jumping, crawling. So a very exciting area of opportunity I see in microrobotics is how to take microelectronics to build efficient and lightweight power electronic systems so we can enable robotic systems at a micro scale.
Mm-hmm. All right. Thank you all. A question for Doug and Susan as our industry representative. So a new technology that is generating a lot of buzz these days is advanced packaging through chiplet integration. This is a new way to put systems together very quickly, inexpensively. But the way we have thought about advanced packaging until now is it's sort of a low value added technology that is best done in low-cost countries. The picture now looks very different going forward. So how do you see this? What are the challenges to really realize the promise of this technology, which is again integration of systems via chiplets, and for that to be a high value added activity that could be done or should be done perhaps on US soil?
Sure, so I'll start with that. As a kind of grumpy old guy, I'll give you a slightly different perspective. I actually think it's kind of what is old is new again type of a concept. When I started at MACOM over 30 years ago, one of the first projects I worked on was a multi-chip module that combines silicon and gallium arsenide and passive devices and all these other kind of things in a little ball grid array, and it was heterogeneous integration, right? But we weren't smart enough to call it heterogeneous integration. And really the phrase was, our mantra as a company was you use the right junction for the function. So we always tried to bring together what would accomplish the individual piece for that optimized little part of the circuit. And we didn't think that was unique, we just thought that was creating compelling solutions for customers. And when you really think about chiplets, that's really all the chiplets are doing, things have gotten more complex, yes, things have gotten more integrated, the solutions our customers want are more complex, but fundamentally the driving force and the driving missions are really the same. And really the challenges are the same. Back then it was, how do I get the impedance of this function to match the impedance of that function? And today it's the same. How do I integrate these dissimilar materials, often dissimilar protocol talking chiplets, and get them to actually communicate with each other to create a compelling solution? And a big piece of that is the whole question of standardization, interface definition, getting lots of companies with competing missions to agree that this is how we're going to do it. So that's a little vision.
I was going to say that. I agree with a lot of what you said. What's old is new again. Heterogeneous integration has been there for quite a while. And packaging solutions are just part of the answer to get into a whole chiplet ecosystem. And we define chiplets as a known good die that you would reuse. That could be combined with other die in a package. And you can come at it from a couple of different directions. You can come at it from where you're taking something that's multiple die on a board, and so package integration, or you can come at it from system on a chip disaggregation. And there's a lot of benefits to both those cases. If you're pulling something together that's on a board, you're putting it closer together, you get higher performance. You can be more flexible in your design, maybe faster time to market, more reconfigurable. If you're coming at it from the system on a chip disaggregation, you could be using the best process for the function that you need now. You could probably have better yield because you're splitting it up into many die. But there are a lot of, in order to do this, we're going to need a whole ecosystem to evolve, because there's a lot of challenges from the EDA to the IP interfaces, as you brought up, to the package solutions, to reliability. And some of the big challenges that we are looking at is how do you guarantee known good die? So you have to be testing everything at probe when you're used to testing it in a package. How do you do a co-design when you have one of the chips and someone else has the other chip that you're trying to combine? So you're going to need design tools that can comprehend that. You're going to have to comprehend all the physical and thermal effects of bringing these die together. There's the interfaces that were brought up, and I don't think there's one standard we're going to need. We're going to need multiple. You don't want to have overkill and have too expensive a package. And then there's the economic challenge of all this, and how do you handle? Right now the companies that are employing chiplets are really making and combining their own chiplets. So they're able to define the interfaces, and they're able to decide where they're going to take yield loss, whether it's at probe or final test of the package. And so these are a lot of challenges if you're going to be selling out there. Who gets the value? Who gets the aggregated value of the solution? There's just a lot of questions. Who when it doesn't work, who's to blame? So it's easy right now if you're just, you're the sole chiplet provider and aggregator, but I think what we want is a marketplace where you can have a lot of different chiplets from different sources, and so this is going to take multi-players, and I think some standardization.
Thanks. Kevin, you told us about the importance of power management at the edge, where the point is not to handle a lot of power in many cases, but to really be very effective at it. What do you see in terms of new technologies? What are the needs? What are the opportunities out there for?
Sure. So let me first start by giving out some numbers of what we need at this scale. For example, our robot weighs about 0.1 gram, and yearly we are trying to build a 0.1 gram circuit that can process on the order of 2 watts of power. So that's a lot of power for very small weight. The first thing that we started to look into when we started constructing the circuit was the weight of each individual component that we can buy off the shelf. And the interesting thing is the vendor always tell us the size of those chips very precisely, but no one bothers to tell us how much they weigh. So clearly, at this point, people don't care too much about the weight or the power density that those chips are. And if you look at traditional power electronic circuits are extremely efficient. They are 90, 95%, 97% efficient. But then when you look at piezo drivers, some of the high voltage circuit, for those scales, the efficiency are 30% or 50%. So I think there's a big margin of improvement. If we start to have more demand of those edge robotic system that requires a lot of power, then we start to create, for example, high switching MOSFET that's very efficient, magnetic component that are very efficient, inductors that are lightweight and being able to handle a lot of power more efficiently out of those. So those are all the opportunities we can think about for microscale power electronics.
Jing, so in the last few years, we've seen a palette of new 2D materials like graphene and others with amazing electronic and optical properties. And so many of us question when are they going to show up in the marketplace doing something useful? So what do you think, when do you think that's going to happen? Who is going to be the first 2D material that's going to impact the marketplace, and on what application?
Yeah, thank you. I think, so graphene appeared first in the 2D family. perhaps, and then the fabrication synthesis of graphene also so far is still in the leading, like a large scale growth of graphene material. In terms of application, perhaps flexible electronics or sensing are the potential areas for graphene. And then in terms of electronics, I think the semiconducting type, these transition metal dichalcogenides are right now, different companies are investigating both in terms of devices and also in terms of growth and fabrication. So those ones could be in the future to be applied in different type of computing devices, like even traditional or quantum or etc. And yeah, I think they are. It seems like they have different areas of applications and will be used in different places.
Great. Ruonan, so chip design is an area where the US dominates. So we lament the loss of manufacturing leadership, but in chip design, the US clearly dominates in the world. So what are the new directions and what are the challenges to be overcome, and how can the US sustain this leadership position in which we are going forward?
Well, first of all, the new directions, I would probably just say two. The first one is obviously the heterogeneous integration, and now the circuit designers really have to decide how to basically divide their system into multiple parts, and then divide that or distribute that into different chiplets, and what kind of process flavors to use. And some of those components could be much more efficient if you just directly push it into the package. Okay, so I think that's a much more interesting problem than before, where we just confine ourselves inside silicon. And also that leads to quite some new problems, such as the multiphysics kind of a modeling and design. So I think for the first time, the circuit designer have to learn much more than just the Kirchhoff's laws and the circuit behaviors itself. And the other really important trend that I saw was how to basically use AI inside these circuit designs. Sometimes you want to build AI little processors directly inside the chip so that in real time, your circuit can better respond to different multi-dimensional change, so that, for example, the efficiency is always at the peak. Say power amplifiers, how do you dynamically adjust the biasing conditions so that for current data and also for the past data, your power efficiency is always at the top. It's a very important new trend. And I think probably what's even more exciting, at least to me, is how to use AI for the actual design. This is pretty successful for digital circuits, but for analog and RF design automation, which has been tried a lot in the past and not quite successful, I think the new AI advances, especially generative AI, could really bring some new possibilities in there. How the AI can serve as a knowledgeable agent to use the simulation tools and then some iterations in a very smart way, and eventually generate some nice circuits. And then eventually about keeping the leadership of US, I would say US has been very strong in, for example, development of the CAD tools, the design methodologies, the new concept. These are definitely the strengths that the US should keep. On the other hand, I think, many people think chip design to be like a game of elites, but I would say the scale is also very important, like generating enough labor is also very important. We not only just have shortage of chips, but we have shortage of people who are in this field. Just one data point, I don't know how many of you are circuit designers in here, but the ISSCC is the top conference for this field. Last year, China published much more paper than US did. I guess it's going to be the same trend this year. I'm not saying that the US has lost the leadership, but I think that sort of shows the scale is also very important, and this is where we should also invest more.
That's very interesting.
Yeah.
We actually saw that China overtook the United States in chip technology at IDM, which is the corresponding conference for devices and technology, already something like 10 years ago. So making huge progress and huge investments. Yeah. All right, also for Susan on that. So in microelectronics, it takes about 10 years for a new technology to go from the proof of concept stage to actual manufacturing, to reach the marketplace. And that's because the demands on manufacturability, reliability, and cost are really huge. Mm-hmm. As we see a future that is going to involve new material systems operating in new ways, it seems like it's only going to get worse. So do you see a way to speed things up, to be able to translate technology much faster from the proof of concept to manufacturing?
And I know that was part of Vladimir's talk this morning on how do we accelerate this and get over that valley of death between the lab to fab transition. So everyone's giving a lot of thought to it. I mean, that's really a lot of the R&D funding for the CHIPS Act is to go towards an NSTC, a National Semiconductor Technology Center, for the purpose of helping with that transition, as well as the Microelectronics Common, which was referred to earlier, that funding, to try and bridge that gap. And I think that that's really what it's going to take, is having, collaborating together, partnering on things, leveraging, people's expertise when they're complementary, working on projects, big technical problems together. But I also feel that having these facilities would be useful, because I know that I've worked at Analog for 36 years doing process development and transitioning into manufacturing. And when you're in a manufacturing environment, that's great because you're using the tools that you're going to be using in the end, so that helps accelerate things. But you're very disruptive to manufacturing when you have to put something down. So there's always that struggle. But if you could have facilities that had maintained that stable equipment with unit process steps you could rely on and stable, reliable flows, I think that would go a long way, where your intended variables are the only variables that you have when you're processing something. So I think that's going to be very helpful. And like I said, I heard a lot of the stuff this morning too about investment in startups and to help bridge that gap. So I think those are the types of things we're going to need.
Yeah, and I agree with Susan that the government funding is a great thing, but when you think about the valley of death, we all walk into it, but who's pulling you out? Right? I mean, if there's not a strong pull to get you out, and a commercial pull that really motivates what you're doing, you won't accelerate what the effort. And recently, we had a lab to fab transfer process where we took a 0.14 micron GaN process from the Air Force lab, and we had working devices within 8 months after beginning that program. So if you're motivated to do it, you can actually very effectively transfer processes and get them up. It's hard to accelerate doing a 1,000-hour reliability test. It kind of takes 1,000 hours, but other than that, your motivation of how you're going to pull it out, commercialize, and what you're trying to get at the end, I think is a really important component.
I think some of the collaborations that we're talking about too, when I go back to this full stack solution, if you have all the layers of the stack working together and co-optimizing the solution, I think that that's going to help accelerate it as well. If you're working in a vacuum and then you take it to your customer and they're like, nope, that's not what I really needed.
Yeah, I think that's one of the places I think Susan and I agree so much on, is that the more system knowledge and end customer knowledge you have to motivate what you're doing, what you're pulling forward, the more successful and the quicker you're going to get it done. Yeah. Often people, I think, it's that pushing on a rope versus getting pulled.
So specifically, a lot of the innovation happens at universities. I think universities are good of bringing new concepts to the proof of concept point, but maybe not so good in pushing beyond. So this is a question for everybody who probably comes here with very different perspective. How can we more effective in bringing new technologies, innovations from universities into the marketplace more quickly and more effectively? Anybody that has experience or insights into this?
I go back to what I was just saying. I think that, working, if in universities, if you're partnered with people that have experience in manufacturing, and whether they could offer complementary skill set or capabilities or give you advice, I think that would go a long way to having partnerships like that, so you're working on the right, like we just said, the right problem.
Mm-hmm.
Yeah, I couldn't agree more. I think strengthening industry-university collaboration, brings a different insight, I think, into the university research, and also helps with that pull, and actually helps on a lot of fronts, especially in terms of the workforce development front, of bringing that talent into industry that'll actually keep it moving forward, which is, I think, an incredibly important thing at this point.
Insight from our academic colleagues?
So maybe I can make just one point, which is I feel that we universities, especially places like MIT, we are never lack of key brilliant ideas, but sometimes there's still a gap between ideas and nice prototype, because the prototype is the previous stage for commercializations. And sometimes I feel that the students, for example, we at universities, each research group has only a few number of PhDs. They are very good in, let's say, circuit design, but they may not be very good in building the whole systems, the whole supporting electronics around their chips. And oftentimes I feel that is where we got stuck when we try to prototype or commercialize. So if that's the place that we can strengthen by, for example, working with the companies, or by places like NSTC, I think part of the goal is also to help prototyping, right? And I think that will be much better.
Anybody else?
So I also feel like, again, the students are very good at doing or inventing one thing, but they really don't have the larger scale picture. So one is for students who want to do startup, for example, on the hardware aspect, having the facilities at the universities or at the companies will be extremely important. And the other thing is, a lot of times students, they learn a lot from going to do internships or finding colleagues in different areas and realizing the technology that they have is very effective in solving some other people's problems. So I think it's just creating a more collaborative environment and support for the student will be very helpful for the student to translate their ideas into a real application.
So another path that's known to be very effective in our domains to bring technology from a university environment to the real world is startups. I know there have been discussions about startups elsewhere in this symposium, but specifically in electronics, startups in hardware have a very hard path ahead, excuse the pun, because they require huge investments and because they take a long time to realize their technology in comparison to startups, say, in software, which will be competing from the same capital from the venture capitalist. So how could we make startups in electronics, in hardware, more successful, more effective? Since this is a path that's been shown to be successful in other domains.
I think that's a very challenging question. I think actually, organizations like MIT.nano are excellent examples. You're absolutely correct. I mean, whether it's materials folks or device folks, to do hardware requires very expensive tools to have state-of-the-art performance. No VC is going to invest in that kind of organization and get them to a point where they actually can produce product, or is going to be very reluctant to do so because of frankly the return on capital. So the ability to leverage multiple organizations together in one entity so that folks can develop their technology is really the only effective way, in my mind, to be able to get that done today.
I think that there's a lot of things that could be done, like the ecosystem could be there to support them with, the facilities for one, like we've talked about, that would be good. If there were elements that they could tap into, like standard, like the PDKs or standardized TCAD, reliability procedures, things that were more available to everyone. I think that might facilitate things. I go back to partnerships. I I think that's going to be key. I know we just had with the NAMC, which I don't know, this Northeast Microelectronics Coalition, we had a meeting recently, and we talked about how could startups benefit from things. And I think, you know, the Startup.nano has a good idea about this voucher program, or giving them nanobucks to help them. So can we lower the entry fee or the barriers for startups in order to, you know, because they can't necessarily afford what big companies can, or access to these types of facilities. So can we enable that through some of the funding initiatives that are coming through the CHIPS Act or other? I think that I heard yesterday also at the Nano meeting, there were some companies that talked, there were a couple of startups, and to see how they leverage these accelerators to not only, it's not just investment and desk space, but it's, you know, connecting them with the right individuals that could complement what they do, that could provide expert advice in technology or application space, because I think connecting all of that is what's going to help. So there's probably a lot we could do in the ecosystem to facilitate that. And there's a lot of good ideas, like just listening here, and I'm sure other places have similar, so if we could aggregate those ideas and amplify the best ones, I think that would be helpful.
Any insights?
Maybe I can add one more point, which is not unique for hardware startup, but maybe for all the startups from the university, and that is basically the visa requirement, or, you know, basically the immigration rules for the international students. I mean, from time to time, I have very brilliant students who have really nice ideas. The students are very ambitious in, you know, commercializing that, but I have very hard time essentially convincing the students to truly turn that into a startup company, and partly because they just cannot. And I think that is a very big loss for US, and they had to go to a major company and start to lose the interest, even if later on they got green card, for example. So I think I really hope this is something that can be changed.
Anybody else?
Oh, I wonder if for hardware-based startup, can there be I think customized help, because it depends on the situation. Usually with software or other types of startup, it might be easier, and hardware type will be harder. If there could be additional help, say from the government or agencies, that might be better.
So hardware companies ought to have an interest, even though they are competitors, but ought to have an interest in supporting hardware startups, right? Because eventually it's a way to get new technology into your company. So should companies have venture capital outfits that will be out there looking for hardware startups to support, because the software venture capitalists will not?
Yes, and we do.
Oh, you do, okay.
I think maybe may come, but we do, and I think that's. But I know that also in that meeting that we had with, you know, how can we facilitate or help startups be more successful? There is that concern about working with a big company that they're going to take your IP before you're ready, yeah. And so you have to figure out how do you have a relationship that's mutually beneficial. Mm-hmm. And I mean, a venture is different. I mean, then you're investing and you're, you know, and we've done that sort of thing. Yeah. But other models for how big companies can work with startups, I think there is that concern.
Yeah, I think like ADI, MACOM, we do investment into small startup companies, as well as have avenues through venture arms, certainly not to ADI's level, because we're not as big as a company as ADI, but that is a viable way to bring in technology, and frankly allows you to evaluate the commercial viability of those technologies over time and increase your portfolio. So it's certainly one of the aims that we have to keep broadening our technology base, just like acquisition is. You know, just seeing we've acquired several startup companies that have great, neat technology that we think we can help bring to the market, accelerate their position in the market. So, you know, join the family and let's all make money on it is basically the theme, right?
Mm-hmm. All right, maybe one final question perhaps for Susan and Doug. So we see these large semiconductor manufacturers all over the news, right? Intel, TSMC, Samsung, They're out there leading technology. There has been a lot of consolidation over the years, so there's only 3 companies that are carrying the leading edge. But there's a lot of other companies, such as yours, that are producing a lot of semiconductors and chips for a wide range of applications. So going forward, how do you see the role of small and medium companies in terms of promoting innovation and opening new opportunities?
I think that when we opened and we talked about all the innovation and the innovation that was talked about this morning, there's a lot more than state-of-the-art CMOS. Mm-hmm. There's so much for RF, for power, for sensors, sensor systems, sensor fusion, intelligent edge devices. I think that, and packaging. We talked about that early on, and even though we said what's old is new again, there's a lot of advances in packaging, and there's a lot of opportunities there. The chiplets, I think that there are a lot. There's an amazing amount of opportunities for small and medium-sized companies.
In fact, I think, for a lot of the revolutionary innovation, it's coming from those medium, second and third tier suppliers who frankly aren't burdened by the bureaucracy of an enormous corporation, aren't fighting the culture of it's not CMOS, right? So inside those larger companies, when you're going against the grain, your probability of success is lower. Whereas if you're in a relatively smaller organization that's still being slightly entrepreneurial and more innovative, you can take bigger risks and you can actually bring more risky things forward and get them into the market, which is, I think, that's really the role the lower tiers are playing.
Excellent. I think we should open now to the audience. I see that there are already some questions lined up in the pigeonhole system here. So let me read the first one and see who wants to handle it. As microelectronic devices become increasingly complex, how can high schoolers and undergraduates learn enough theory to A, feel confident pursuing the field further, and B, contribute meaningfully? So,
I'll start with that. I think the first thing is folks who are in high school or undergraduates have to understand you can actually have a career in microelectronics and be successful and actually have a life and support your family and all that kind of good stuff. Because I think a lot of folks, right, you play with your phone and you see, gee, I can write an app and I can be a millionaire. That's what everyone wants to do. And they're just totally unaware that all the hardware behind that thing. So one of the things we do is we send our engineers out to the local elementary schools and high schools to be tutors and to help and show people, golly gee, you can actually have a career in this field and have that interaction. If you don't have that interaction, how would they even know it exists?
Mm-hmm. Any comments, Jing?
Yeah, I actually have some thoughts on this. So actually, every summer, I actually, our group, we receive some requests of high school students. They would like to have some intern experiences. But nowadays, since we work on experiments, it's very hard to have students below age younger than 18 to be in the lab. But I feel like when our kids are young, we took them to Home Depot on Saturdays. Actually, they have these places where you can build things yourself. I think that's actually a very good model if companies would like to open up, have opportunity for summer intern for these high school students, have the training. This will be really later be the workforce development for the country in the future.
So Analog Devices did do something recently with high school students, and we had them in as an intern program. And there is the program that got started by the NEMC. Tomas Palazios was leading it to get freshman and sophomore interns into companies so that they get broader exposure. And I think that that's really valuable to get them to see what we really do. But I also caution that we want to make sure that it's a positive intern experience, and you want to make sure that you're getting them the right mentors. And I think a lot of times we think, what can we get out of this, labor, and I think that we should be trying to impress them more than seeing if they're impressing us.
Mm-hmm. I see a great question there. Yeah, the last one on that list. So what are MACOM or ADI doing with respect to environmental sustainability in semiconductor manufacturing? What are the biggest challenges? This reminds me of a panel that I participated last year where I learned that Apple does a very detailed study of their carbon emissions throughout all their operations. And it turns out that the biggest, by far, consumption of carbon in terms of Apple is the making of the chips that go into the products. That consumes more carbon than the operation of all the devices around the world combined in any 1 year. So it's truly extraordinary. So semiconductor manufacturing is a really energy-intensive operation. So what is ADI? What are ADI and MACOM doing to try to ameliorate this?
So we come at it from a couple different. We definitely have a whole group focused on sustainability. We have target goals for our company in terms of our facilities, in terms of water usage, electricity. How can we make them greener? So just from a manufacturing perspective, but I know that our CEO Vincent Roche is very passionate about this and saving the world and the planet. And we, a lot of our products too, emphasize, the sustainability going for the electrification and automation. So we're coming at it from a lot of different perspectives here. And I think that it's challenging sometimes when you think about the life cycle of where did that silicon wafer come from and where did it fly to get processed, and then we maybe process it in Taiwan and then ship it somewhere else to get packaged. So there's a lot of carbon, that we need to be addressing.
Yeah, I think without a doubt. I mean, clearly operating fabs are environmentally challenging operations. I can say when I started, I'm actually a material scientist, and I actually started working on gallium arsenide. And up in Lowell, we were bringing in, I don't know, something like 350 metric tons of arsenic into one end of the building and gallium arsenide going out of the other end of the building. And we had this funny requirement that the outgoing wastewater of the plant had to have lower arsenic concentration than the incoming wastewater of the city of Lowell, because we're all in New England, and golly gee, arsenic is in the ground here. So as companies, we have an enormous set of environmental goals that every year we're achieving, whether it's lowering your electricity usage, lowering your water usage, making what's coming out of the end of the pipe cleaner, using less solvents, using less acids. Everything is about how do I become more efficient and more environmentally friendly, without a doubt. I mean, but it's a very, very challenging area that I think almost every fab could use help in, because it's a very, very challenging subject.
If you could give me the last question that was there. This one, yeah. It seems US hardware companies I got covered. This one. Want to recruit talented international students, but also don't want to sponsor them for expensive visas. How can they reconcile these conflicting interests?
Is that true?
I don't think that's true.
I don't think that's true.
Okay, it's not true. Good. Answered. Can you give us some more?
I mean, it's challenging. I mean, it takes time, but.
Yeah, and Frank, I mean, really, it's not more of a visa problem as often it's an export control problem in regulations the government has placed on who we're allowed to transfer knowledge to, which is preventing us from bringing folks in. It's not because of a desire on the company's part to bring people from around the world.
I think this point has been made extensively in the last 3 years, where we have been talking about the CHIPS Act and how to promote semiconductor manufacturing in the US. The need really to open up the doors and to bring the best students from all over the world to join our ecosystem here in the US. So I think the message has come loud and clear, and I want to believe that it's being acted on.
Yeah.
Mm-hmm. All right, there's a question there. Thanks for these perspectives. I'm curious to know what might be possible for nanotechnology in the next decade. Bruce wants to handle that. Jane, perhaps? Yes.
Yeah, I think what we are working, like everyone, we are working on now, like these devices are really getting into really small nanometer regime. For my own perspective, I think in terms of materials, actually dimension create a lot of new opportunities. Like when it's confined into 2D, or when it's even further confined into 1D or 0 dimension. And I see that actually a lot of new opportunity. Like for example, the wide bandgap semiconductor, when material are bulk 3D make into 2D, it could be the same material, but it could be completely different structure and property. So there are a lot of opportunities there. That's from the material aspect. Yeah.
Well, thank you. And with this, we're going to bring this panel to an end. Thank you for your interest, your attention, and your questions. And thank you to my colleagues for a very interesting discussion. Thank you.